This is Group 3's Data Analytics mini project for ultra-wideband signal classification as well as range prediction. We first begin with data loading and setup, where we import the libraries used in the solution, as well as read the CSVs and load them into a data frame. Next will be data preprocessing, where we use feature engineering to derive statistical features from the 1000 plus CRR columns. The 1000 plus CRR columns are then dropped to reduce the dimensionality of the dataset. To further process the dataset for machine learning, the following measures are in place. Duplicates are removed, and rows with missing values are dropped, because imputing might introduce bias. Constant columns are also dropped as they don't provide predictive value. Categorical features are converted into numeric values for the machine learning models. The dataset is further refined by selecting the most relevant features to improve model performance and reduce overfitting. The steps involved here are to split the features and the target, with the target variable being NLOS. We do a mutual information analysis and we keep the features in the top 75%. And we also do correlation filtering and low variance filtering to remove highly correlated feature pairs as well as near constant features. The features are then normalized using z-score normalization, and class imbalance was addressed with synthetic minority oversampling technique. However, because the dataset was balanced to begin with, the smoke didn't really have an effect. Then we plot a histogram of the normalized features to ensure that normalization worked, as well as a correlation heat map to identify any features with high correlation or low variance. We also apply PCA to reduce feature dimensionality while retaining most of the information in the dataset. However, the variance visualization shows that we need a high number of principal components, hence we did not adopt this in our final solution. We move on to data mining for model training and evaluation. The dataset is split into training and testing sets with an 80-20 split, because our dataset has very high number of samples, and 20% for testing was enough to garner valuable insights. We also use stratified sampling to ensure class balance in the split. Now we move on to the first objective, which is LOS and NLOS classification using the random forest classifier. The flow is that we train the model, then we make predictions on the test dataset, then we visualize the feature importance, and then we do a performance evaluation using accuracy score, confusion matrix, and the classification report. Through visual analysis of the feature importance, we can see that features like FPIDX and FPAMP1 had very low predictive power, hence we decided to manually drop them. We trained the model again and then we plotted everything again to visualize the impact of the removal of features. And it can be observed that the removal of the two features had almost no effect on the accuracy, so dimensionality reduction was achieved without detrimentally affecting the accuracy of the model. We also repeated this with the neural network multi-layer perceptron classifier, and you can see that the accuracy is slightly lower. But for data visualization, we plotted out the confusion matrix for both the random forest classifier and the neural network classifier to compare their performance. From the confusion matrix, we can see that the random forest classifier slightly outperforms the neural network MLP classifier. Next, we move on to the second objective, which is predicting the range of LOS signals. The same data preprocessing steps are applied for the regression models, but the data is split into LOS and NLOS samples, which allows us to train separate models for both scenarios. The dataset is also split 80-20. For range prediction, we tested several different algorithms to see which one performs the best on the data. The four algorithms used are random forest regression, XGBoost, and LightGBM, which are gradient boosting algorithms, as well as k-nearest neighbors. We begin with the random forest regressor and we evaluate its performance with mean average error, mean square error, root mean square error, and R-square value. And these are the findings. Now we repeat the same steps for XGBoost, KNN, as well as LightGBM. For data visualization, random forest regressor had the best performance out of the four regression models. So using random forest regression, we plotted out the actual versus predicted values in two scatter plots, with one being color-coded by RxPACC, which is the feature with the highest feature importance. And these are the findings. So we can see that most of the points lie along the red line, which is ideal. We repeat the same for NLOS signals. And these are the findings. And with that, we end our presentation. Thank you.